Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists where I do quick turnaround videos for academics. Not for academics. Well, I could do for academics if there are any out there that want them. For educators and their students. So if you'd like me to make a video for you, just comment below any of my videos or drop me an email. We're going to talk about subsequences. Why are we doing that? Well, we're going through the 3 C's in analysis. What I saw described as the 3 C's. Continuity of functions we've done, we're heading towards compactness and we need an understanding of subsequences. Okay, so that's good. We talked in the previous video about just a sequence, which this is an example of one. We have that notation to indicate that the sequence is A1, A2, A3, A4, and AN is given by, say, 1 on n. So here we'd be thinking of the sequence 1, a half, third, a quarter, etc. Okay, so what's a subsequence? Well, a subsequence of a sequence what is it? Consists of sum of the terms in the sequence in the same order. Now you can handle just picking out a finite number of elements to make up a subsequence, but I mean generally you're talking about picking an infinite number of terms out, because if you have a finite number of terms, the convergence and issues like that become trivial. So just in the back of your mind, you're sort of thinking generally infinite number of terms. So what's an example for, let's say, for that AN above? Well, we could construct a sequence 1, a third, a fifth, a seventh, etc. That would be a subsequence of AN. Okay, now there are a few things that come immediately, I suppose. If you have a convergent sequence, well then every subsequence converges. So that's one interesting thing. So I suppose an example, I'm not proving anything here, but for AN above again, we might look at, if I just took 1, say 1 on 2, 1 on 3, I'm just doing here 1 over the primes, well, that will actually converge just like AN, just like the sequence converges, and in fact it'll converge to the same limit. On the other hand, if you have a divergent sequence, well, that doesn't necessarily lead to convergent subsequences. Okay, there is one theorem that is important here, I'll just mention, that picks up on this idea of boundedness, which we talked about in the previous video. So this is the Bolzano-Weierstrass Theorem, and it dates back to, I think, around 1840, and it says every bounded sequence in, well, there are different versions, but let's just say in Rn has a convergent subsequence. and maybe I'll just put up like a little sketch of the proof, or one of the proofs, a proof. Imagine you had AN, so that that equals, the sequence A1, A2, A3, and here all the AIs are elements of the reals. And let's just say the positive reals, just do the positive to make it simpler for this sort of sketch of the proof. Because it's bounded, since it's bounded, there must exist a integer d that appears infinitely often. So what do I mean by that? I mean this number here, A1, that could be 5.2. This one could be 100.6. This one could be 3.7. Now, remember it's bounded, so we can't just have the AIs going up and up and up, or going up forever. Because they're bounded, there must be an integer that appears infinitely often. So I'm going to call that D. And then next, there must be a first decimal place in A1, A2, A3, etc. that appears infinitely often. Call it D1. So what I'm saying is if we go back up to here, this one might be 5.3, 10.4, 11.6, whatever. But if you look at the first decimal places, I think it was 356, because it's an infinite infinite sequence, we can pick the one that appears infinitely often. What I should actually say is, back here actually, what I should have done is, to make this a bit, is say remove all AI that do not have integer d. So here you can see we start to create the subsequence, because we get rid of all the ones that don't have d. So at this point, our sequence, which it may be A1, A3, A7, A200, will go on, but all of them will be d point something something something, d point something something something, d point something something. So that's our subsequence. Now once we do here, so remove all without D1 in first decimal place. And so here, now we're down to D dot D1, D dot D1, all the ones like that. And we can just keep repeating this process, and then continuing, we will get a subsequence that converges to D, D1, D2, D3, ... So, I mean, I don't want to get too wound up about it. Don't worry if you have trouble with that. But I just thought it's worth throwing that up. That's all I wanted to do, is to say about subsequences. I think we've got one or two other little ideas that we need to discuss, and then we can get to compactness. If you've got any questions about anything mathematics, comment me below any of my videos or drop me an email, and I'll try and help you out if I can.